Hello everyone. Today let us look into radioactive methods of geophysical exploration. What is radioactive methods? Radioactive methods help us to identify deposits that are associated with radioactive elements, especially radioactive minerals. There are several common radioactive minerals that exist below the surface of the earth. There are about 50 naturally occurring radioactive isotopes. However, most of them are rare and they are also very weakly radioactive, right? So, we are actually living in the earth where there is some natural radiation due to the presence of radioactive isotopes in the rocks and soils below the surface of the earth. This method is mostly used in geological mapping of different rock types. How we are identifying the different rock types? We are able to identify different rock types based on their radioactive signatures, right? Some rocks may have more amount of radioactive isotopes, some rocks may not have any radioactive isotopes. So, we are able to map the surface of the earth based on the radioactive signatures. Since, as you can understand, this method is mostly used to target some specific radioactive minerals. This method is not very popular like the other methods which we have seen, since the application is limited to mineral exploration, right? However, since nuclear minerals are strategic minerals which are in need, which are also very rare, hence radioactive methods are very popular to explore such nuclear minerals, right? What is radioactive survey or radiometric survey? What we are going to do here is the measurement of natural radiation which reaches the surface of the earth, right? The measurement can tell us about the presence of radioactive minerals below the surface, either in the soil or in the rocks. Radiometric method measures the distribution of all the radioactive elements. The most important radioactive elements are potassium, thorium and uranium, right? The method is not capable of understanding the presence of radioactive elements beyond several meters below the surface. The method is highly suitable to understand the presence of radioactive minerals in the top few centimeters of the surface. But when radioactive elements are present in the top few centimeters, right, let us say it is only 50 centimeters, the presence of radioactive elements in the top 50 centimeter in fact indicate the presence of radioactive deposits much below that, right? Since there is a radioactive deposit below the surface of the earth at greater depth, the leaching and mobility of this is causing natural radiation at the surface of the earth, right? Routinely used in mapping, right, to tell where certain rock types change. However, this application is much more popular in boreholes, which we are going to see later, right? What we are seeing now is the surface radioactive method. That means we are going to carry out the measurement on the surface of the earth, whereas in borehole logging, we are going to make the measurement in a borehole. So, borehole measurement of radioactivity is much more popular, especially for water well drilling and also in oil exploration, as well as identifying potential pay zones in oil fields. There are several minerals, right? These are all the different minerals that contains radioactive elements of potassium, thorium and uranium, right? This slide I have put up to indicate how these radioactive elements are very commonly present below the surface of the earth. Why? Because they are present in all these minerals. These minerals are very common minerals. For example, if you look at the first one, orthoclase and microcline feldspars. Feldspars are one of the important rock forming mineral which is present almost in most of the rocks, even the common sand which we all of you would have seen, the sand also has got some particles of sand. Most of it is quartz, part of it is feldspars. So, if feldspars are more, there will be some radiation due to potassium, right. So, these are all the different minerals which are present in most of the rocks that occur on the surface of the earth, right. And since these three elements are very important and they are radioactive, which are present in most of the rocks, this trilinear diagram indicates the domination of a particular element in different types of rocks. For example, potassium is present in most of the igneous rocks and specifically in pegmatites. So, most of the igneous rocks consists of potassium, and whereas monazite rock are rich in thorium and some carbonates are rich in uranium, right. Many times radioactive methods are preferred to understand the or to identify or to explore for uranium, which is a strategic radioactive element, but the measurement which we make is obscured by the presence of potassium, because potassium isotope is not going to be very useful. On the other hand, uranium is a very strategic and important radioactive isotope. The identification of uranium deposit many times may be obscured by the presence of potassium, right. So, in radiometric survey, potassium is considered as a noise. Presence of the radiation which might have been generated by potassium is a hindrance, is a nuisance for us. So, it is considered as a noise. So, after seeing something very general about the minerals and rocks that is containing radioactive elements, let us pass on to what are all the units which we normally use in radioactive methods. One of the common unit which we often use in radiometric survey is electron volt, which is referred by small letter E and capital letter V. Electron volt is given by this equation, where the energy unit corresponds to the acceleration of particle having a change of electron through a voltage difference of 1 volt. For a voltage difference of 1 volt, what will be the charge of electron, right? That is what is known as electron volt. The other unit of measurement is known as Curie. 1 Curie is equivalent to 3.7 into 10 power 10 nuclear disintegrations per second. If the nuclear disintegration is equivalent to 3.7 into 10 power 10, then it is called as 1 Curie. Then becquerel. Becquerel is the international unit of activity of measurement. 1 becquerel is equivalent to 1 nuclear disintegration per second. This is how Curie and becquerel are different. Here, so many disintegrations per second. Here, it is 1 disintegration per second. Then, Röntgen is another unit. It is a unit of exposure dose when radiation is X-rays or gamma rays. 1 Röntgen is the intensity necessary to produce a electrostatic unit of charge, which is equivalent to 2 multiplied by 10 power 9 electrons per cubic centimeter of air. Right? These are all the 4 units which are often used. Very often we use electron volt is one of the very popular unit that is used in radiometric survey. What is radioactivity? Just to give you some glimpse, I have put radioactivity. All of us are aware of what is radioactivity. It is the disintegration of atomic nucleus that gives rise to a phenomena known as radioactivity. That means converted from unstable stage to stable stage. A For example, a mineral which is radioactive is unstable, slowly it is getting converted into a stable stage. One of the greatest advantage of radioactivity is the phenomena of radioactivity is unaffected by any other agents, maybe increase in temperature or pressure or an earthquake or a landslide or a tsunami. Nothing will change the way in which the disintegration takes place. So, which is of greatest advantage. That is why the radioactive phenomena of radioactivity is also used in understanding the past. That means we are able to date the time at which a particular element would have formed, right. That is another advantage. During the process of disintegration, energy is released in the form of three types of radiation, which is known as alpha, beta, gamma. Why we are looking into this basics? In radioactive methods, we are going to measure the energy that is released. That is what we have seen on the previous page. The energy that is received is going to be measured by one of these units. So, the energy that is released is going to be measured in radioactive methods. These are the three ways of disintegration, that is alpha, beta, gamma are the three types of emission that takes place during the disintegration, right. Out of this, gamma ray is much more capable of traveling or reaching the surface through the thick soil zone at the surface of the earth. Because of this fact, right, alpha radiation can be even stopped by a simple paper. A sheet of paper may prevent the alpha radiation, right. Beta can be stopped by some thin aluminum plate, a thin aluminum plate. This is with a sheet of paper, beta can be stopped with the aluminum plate, whereas to prevent propagation of gamma radiation, right, you need a very thick dense material. That is why today in nuclear power plants we use a very thick concrete shell around the inside, the reactor is within a maybe a lead vessel which is also covered by a thick, maybe 1 to 1.5 meter thick concrete shell is constructed, right. So, that is to prevent radiation. So, out of this, since this may not reach the surface of the earth, alpha will not reach, beta also may not reach, only gamma radiation can reach the surface of the earth from the subsurface. So, gamma radiation is generally measured in radioactive methods. What are all the instruments we use to measure radioactivity? The three major instruments that are used, which most of us would have studied in our schools, right. One is Geiger counter or Geiger-Müller counter. Number 2 is scintillation counter. The third is gamma ray spectrometer. Out of these three, the first one simply measures the counts. The second one also simply measures the counts per time. That means, in the first two methods, we are only measuring the total counts that reaches the surface of the earth, which may be due to any of the radioactive elements that are present below the surface, right. I had told you there are about 15 radioactive elements, 50 radioactive elements. Out of that 50, 2 or 3 are very important, that is uranium, thorium and potassium. The first two methods can measure only the total radiation that is reaching the surface. Hence, we may not be able to discriminate whether the radiation is due to uranium or thorium or due to potassium. To overcome this, there is a third method which is known as third type of instrument, which is a spectrometer, gamma ray spectrometer. That means, it is able to measure the gamma radiation in different spectrum based on the energy level of the radiation. Because of this, we are able to separate the spectra of gamma rays that is generated from all the radioactive elements such as potassium, thorium, or uranium, right. That means the gamma ray spectrometer is able to measure the spectra of gamma rays that is generated from the different elements, right. Here is a picture of a popular gamma ray spectrometer, handheld meter, right, a very compact meter, right. And here you can see the results as we walk. It shows us the results of uranium, potassium and thorium, right. You can see the meter is clearly giving. In the case of potassium, the radiation due to potassium will be very less, so it is given in percentage. And in the case of uranium and thorium, you can see approximately the soil beneath the surface has about 4 milligram per kg of uranium, about 10.3 milligram per kg of thorium, right. So, this is how we are able to quickly assess the concentration of radioactive minerals below the surface of the earth using gamma ray spectrometer. After having looked into the instruments, let us see how the survey is carried out. Survey is can be carried out both on the ground as well as from the atmosphere, right. Survey can be carried out from the surface of the earth and also from the atmosphere. We have already seen alpha particle will not be reaching the surface, beta also may not reach the surface because a thin aluminum sheet itself can arrest the beta rays or beta particles. Sometimes some small amount of beta radiation may reach the surface, but it can be measured only by ground based survey, right. Whereas gamma radiation can go into the atmosphere too. So, gamma radiation can be measured also from the aircraft. So, radioactive methods can be carried out on the surface of the earth as well as from airborne instruments, right. So, in airborne survey, generally we use scintillation counters or gamma ray spectrometers, right. The advantage of gamma ray spectrometer is we are able to get the spectrum of gamma ray, right. This is done by carrying a gamma ray spectrometer in a helicopter or in a aircraft. As you can see, a aircraft is flying over the surface of the earth. It is able to pick up the uranium radiation due to uranium, radiation due to thorium and radiation due to potassium. How? Because this instrument spectrometer is capable of getting the spectra of gamma rays. So, we are able to get the concentration of approximate concentration of uranium, thorium or potassium, right. But even the gamma radiation may not travel to greater height. So, it is always better to fly at the lower altitude to get better results, right. Normally, we fly at an altitude of about 100 to 150 meters, right. Also, the height of the plane has to be maintained constant to overcome the error, right, because when the flight goes above here and flies at a lower altitude, when it goes above, the signal which we receive may get reduced. When we fly lower, we may be capturing higher amount of signals, right. Also, topographic variation. So, here there is a hill, and because of the hill we need to fly, right. As far as possible, the height of flying has to be kept constant. So, these are all some issues which we have to overcome, right. If helicopters are used, we can fly at a very low altitude, right, and also at a lower speed, so that the radiations are picked up with greatest accuracy and advantage, right. Usually, the flight lines are about half a kilometer to 1 kilometer apart. So, this is how we fly to cover a area, right. And the pattern of flight, one is like straight line as I have drawn, or sometimes we may also, suppose if you know the target, we can also fly in the form of a circle to reach the target. This is known as contour or rim flying. These are all the two common methods. So, mostly we use straight line flying as I have drawn here, right. Let us see some results. So, here is the results from gamma ray spectrometer, right. Here you can see the energy spectra for potassium, uranium and thorium. So, here is the energy level, right, electron volt or milli electron volt, right, and here is the count rate, right, and it is well known that at this energy level, whatever is peaking is due to potassium. We know at this energy level, whatever is the peak, that is due to uranium. So, this is how we are able to segregate the uranium distribution as well as thorium and potassium distribution. So, intensity of radioactive elements are identified from the nature of the curve, which we can create by plotting the energy level with respect to the count rate, right. So, gamma ray spectrometer thus is capable of producing this energy spectra, that's using which we are able to understand the concentration of radioactive elements below the surface of the earth, right. Coming to the interpretation, as we had seen just now, after the reading is taken, a graph is plotted against energy and relative count rate. A sharp localized anomaly higher than the background value indicate the presence of radioactive elements, and also shape and size and width of the anomaly depend on the radioactive elements, right. If you have high concentration, suppose you are taking a measurement over a uranium rich rock, obviously the anomaly will be much higher, and also the shape and size of the ore body also affect the control the anomaly which we measure. Then gamma rays emitted show up sharp emission lines on the spectrum output. That means gamma rays are the one which is much stronger, which can be easily picked up by the gamma ray spectrometer. Intensity of spectrum level actually reveals the concentration of elements, right. Suppose if the energy level that is corresponding to uranium is much higher, that indicates uranium deposits are present below the surface of the earth. So, typically these are all the energy level that is generated due to potassium, thorium and uranium. Total is approximately this much. That means, if you take the typical values, the count per seconds will vary between this to this for potassium, for thorium, and this is for uranium, when the rock has got so much of potassium, right. That means, when the potassium content is about 5%, it is able to produce only 450 counts per second. On the other hand, if in the case of uranium and thorium, it is even if small amount of uranium and thorium are present, that means of about 30 to 40 ppm parts per million, that is able to produce so much of counts per second. That is why in the display I showed you, right, the potassium is expressed in percentage, whereas the remaining was expressed in terms of ppm, right. And we had seen such a diagram, right. That means, here is the energy level in milli electron volt, and here is the counts per second or counts per channel, and each peak corresponds to one particular element. For example, here this is the energy level for uranium, this is the energy bandwidth for thorium, this is for potassium, right. So, we are able to also corresponding to the counts corresponds to the concentration, as we have seen previously, right. So, since we are getting the spectra of gamma ray, we are able to differentiate, this is the counts per second for potassium. So, using which we are able to get the concentration of potassium. Similarly, here this is the counts per for uranium, we are able to get the concentration of uranium. So, this is the advantage of gamma ray spectrometer, whereas the first two instruments Geiger-Müller as well as scintillation counter will give us only the total gamma ray, which is not very helpful, but at least it will give us a clue whether we can deploy gamma ray spectrometer at a particular place, right. So, this is how we are able to get the spectrum and also get the approximate concentration of these elements by carrying out the survey at the surface of the earth. What are all the applications of radioactive methods? We already know radioactive methods are mostly used to identify radioactive minerals, right. Broadly, radioactive methods are used in environment because mapping of radioactivity over the surface of the earth help us to know occupational safety, right, whether the place is livable or not, right. So, the radiation which a person receives have to be much lesser. So, here are some numbers. Radioactive minerals account for so much of or 8% of the radiation dose a person typically receives in a year, right, including medical exposures, right, and very much it is in use for petroleum exploration because radiometric methods shows regions of geochemical and geological changes. This helps us to directly understand the possible locations of oil and gas reservoirs. Obviously, as we have been seeing right from the beginning, it is very much in use for radioactive mineral exploration, especially very much it is used for uranium mineral exploration, right. And broad applications are mineral exploration. Also, it is only radioactive gas is radon. Radon can also be measured using some special instruments, radon anemometer, that help us to identify major structures below the surface of the earth. Suppose if there is a major fracture which is a fault, right, radon gas will try to escape through the fractured zone. Radon gas may be absent here, it is absent, whereas here it is present. That help us to delineate major fracture systems, right, and help us to understand zones of water saturation. As I told you, the fractured zones generally have higher radioactive counts. Radioactive anomalies also indicate the presence of oil fields, and by tracing the radioactive halos, we can identify possible locations for oil exploration. So, and now I will come down to some specific case studies. Here is the Mars, right. The planet Mars was mapped using a gamma ray spectrometer. Here you can see the potential variation on the surface of the Mars, right, has been mapped to identify possible whether there is any presence of water by using gamma ray spectrometer over the surface of the Mars, right. That means, if you look at the scale here, anything of this color is likely to have higher amount of water, right. This is how they have put the scale, but there not much of presence of water in the Mars. Maybe this one can have little bit, right. This blue color shows the presence of water, right, using gamma ray spectrometer. Right. Then here is a lunar mission, right, for detecting water. So, how we are able to detect water? We are able to measure the neutrons, right. The presence of neutrons, we are able to understand the abundance of hydrogen, right. So, by measuring the neutrons, it is possible to calculate the abundance of hydrogen. Thus, inferring the presence of water. So, we are able to infer the presence of water in Mars as well as in Moon using gamma ray spectrometer. From other planets, now we will come down to the Earth. Here is an example wherein they have deployed gamma ray spectrometer over a large area to understand the distribution of uranium, thorium and potassium. So, here is a trilinear color chart, right. Wherever you have blue tinges, right, they are all uranium rich region, and this color, so this pink color region is of not importance because they are all dominated by potassium, and yellow zones are thorium. So, here the entire region has been mapped with regard to the concentration of uranium, thorium and potassium. This the study carried out by Geological Survey of Canada. Here is a study in which they have tried to understand similarly how the potassium concentration varied over a large area, right. Potassium is released due to alteration of some feldspar minerals which has got higher amount of potassium. They could map the concentration of potassium using gamma ray spectrometer. Here in a region in Egypt, they have used gamma ray spectrometry, right, airborne gamma ray spectrometry to understand the possible presence of uranium deposits. That means they could decipher uranium rich formations. So, here is the scale, right, all this pink color are possible locations of uranium deposits, right. They had also combined with some other remote sensing method. They have come out narrowed down to possible uranium deposits, right, which they have published in their article, right. So, these are all some of the case studies that would have given you some idea about the application of radioactive methods. On the whole, radioactive methods are helpful to map the presence of radioactive elements. Indirectly, the presence or absence of radioactive elements also help to understand the change in the rock types. So, radioactive methods are useful in understanding the changes in the rock types in geological mapping and identifying radioactive mineral bearing deposits, especially uranium bearing deposits, and also to map water content based on the presence of neutrons. Thank you very much.